some small technical problems with Panopto and are very soon ready to begin the next plenary lecture. It's given by Dr. Olav Brienbjerg, and well, you can read his full bio in the program, but briefly, among other things, he worked as first assistant professor and associate professor and then full professor at Technical University of Denmark from 1991 to 2021. And there, part of the time, he was head of the electromagnetic systems group and DTU ESA Spherical near-field antenna test facility. And he also founded the DTU electromagnetic test center. And in 21, he founded his own independent research company, EIMaReCo. Well, I think we could get started. So the title of this plenary talk is High Accuracy Satellite Antenna Testing Employing the Spherical Near-Field Measurement Techniques. The floor is yours, please.
Thank you, Henrik. Good afternoon, everyone. So I would like to start by thanking Henrik Berlin as chair of the Technical Program Committee and the general chair of the conference, who's already discussed it, for giving me the opportunity to talk here today. I like very much the URSI Electromagnetic Theory Symposium for its focus on basic electromagnetics. And it was also when this conference, that when it was held in Copenhagen, that became the kickoff for a lot of international collaboration between my former department at the Technical University of Denmark and people around the world. It's a long time ago. It was in 1962. I wasn't there at that time, but talking with Professor Juslange this morning, I realized he was there at that time. Well, anyway, and I hope you can hear me also up at the back, otherwise you give me a sign. Okay, very good. So, let me start this presentation, and the key word here is accuracy, or even high accuracy. So I'll start by giving some examples of satellite missions which had a very stringent requirement on the measurement accuracy for the satellite antenna testing. So one example here is the so-called soil moisture and ocean salinity mission. It's a mission within the ESA, the European Space Agency's Earth Observation Program. And as the name of the satellite indicates, it measures the soil moisture in the ground and the salinity in the oceans. To this end, it carries a radiometer antenna working at 1.4 gigahertz. And in testing this antenna in the anechoic chamber at the Technical University of Denmark, the demand on the measurement accuracy was the following: within the top 3 dB of the pattern and within 1 sigma confidence interval, 0.05 dB on the magnitude of the pattern, and 1/3 of a degree on the phase of the pattern. And if you have been involved in antenna measurements, you know these are stringent numbers. Another example is the Sentinel-1B. Here we didn't measure the antenna on the satellite, but the probe which was used to calibrate the antenna on the satellite, and that had even more stringent demand on the measurement accuracy. You see, this is the top 3 dB part of the pattern and within a confidence interval of 3 sigma. Other examples are the biomass, which was just launched this April, and the method, which will be launched later this year. So in all cases, you see how it could look in space, and then the pictures from the anechoic chamber, where we did the measurements. So, looking at these numbers, you can see it's not unfair to say that the demand for very high measurement accuracy is of the order of hundreds of a dB. 100ths of a dB of the order of, I should say. But not at 100 dB, but of the order of 100 dB. Even over here, if you want to determine gain to 0.1 dB, you need the gain reference antenna by which you're comparing to have an order of magnitude better accuracy. So we are down to these numbers. Okay, so let's just agree on some terminology. Precision. What is precision? Precision is a measure of the quality of the measurement process. If you have high precision, you are in control of the random errors, and that means that you measure the same thing, or more or less the same thing, each time. But you don't necessarily measure the right thing. Accuracy is the quality of the measurement results. So here you need to be in control of both random and systematic errors in the measurement process to have high accuracy. Now, the precision you can check individually or internally to the facility. You can do repeatability measurements, reproducibility measurements. You can change parameters in your measurement setup, and in this way find out what is the level of the random errors. But for accuracy, you can only check it externally by comparing with independent simulation results or by comparing with independent measurement results. And some examples of these are the following. So we took a standard gain horn here, backed by a metallic plate. We did measurements at this particular frequency. This is the copolar pattern in the forward hemisphere. The forward hemisphere projected down the aperture of the antenna, so it's a UV plot, as we call it. And this is the cross-polar, and this is the cross-polar pattern that we have here. And this is the main beam directivity. And I wouldn't normally put 3 decimals on a measured quantity because the measurement accuracy is never that good. But the thing is that when we put this into a simulation software, which is a commercial program with D, which is based on an integral equation in the moment solver, you can see we got a simulated main beam directivity, which differs by less than 1/100th of a dB. So both things must be right since they agree so well. And when you look at the radiation pattern, you can see no difference at this scale on the copolar. On the cross-polar, you can see some differences here compared to here. But we find the equivalent error signal, which expresses the difference between the two patterns, is more than 60 dB down. Now, this is at one particular frequency, and as you know, at one particular frequency, you can make everything happen. You can have 2 curves and they cross at some point, right? So here they are. So if we look at the result over a range of frequencies, we have here the antenna from before. We also have another antenna. Now we put an absorber here. And then over here, over this frequency range, we measure the directivity for each of these and compare it with simulations. So for this one up here, the solid blue curve is the measurement, and the dotted blue curve are the simulation. And for the red, solid line is measurement, dotted line, simulations. And the maximum difference you see in that pattern is 0.025 dB. Another thing you can see here, there's a big difference between using a reflecting plate or an absorber behind the antenna. Here you have a very strong variation of the field because it's an interference of the direct signal from the antenna and the reflection from that plate. The reflection from the plate is eliminated here, so we only have the direct radiation from the aperture, and as you can see, it goes almost like the theoretical 1 over lambda squared. Now these were simulations. We can also compare with other measurements, and to this end, the European Space Agency has developed a series of so-called validation standard antennas, VAST antennas. And these antennas have been used in many measurement campaigns in Europe. Bring the antenna around different measurement facilities, do the measurements in the individual facilities, and then compare the measurement results. And the antennas are very stable, mechanically and thermally, so whether you put it in your measurement facility oriented like this, or like this, or this, with respect to gravity, they don't bend, they don't tilt, they don't do anything, and over a range of temperatures, also the expansion thermal expansion is very small. So if different measurement results are obtained, it's not because of the antenna changing, it's because of the facility. And also the European Association on Antennas and Propagation has a series of validation standard antennas, and these antennas can be leased or lent from these organizations if you have a measurement facility that you want to validate. One example of using this millimeter vast antenna is this campaign here. So what we see is the pattern in the offset plane. So that's the plane which is parallel to the screen here. And we see results from 2 spherical near-field antenna measurement facilities and 3 different compact antenna test facilities. And you can see from a large distance they look more or less the same, but if you look closer, there are some notable difference in the top of the pattern and the side lobe level of the pattern on the cross polarization. And these differences are very revealing for the individual facility in assessing how they could possibly improve the measurement process, the measurement instrumentation, the measurement process, and so on. So, the title says Spherical Near-Field Antenna Measurements, and this is what I want to focus on. And my claim is that this is the most accurate technique for experimentally characterizing radiation from antennas, because spherical near-field antenna measurements combine a set of advantages. First of all, we do it in shielded rooms, so there's no external interference. The shielded room is lined with absorbers, so we measure mainly the direct signal between the antenna on the test and the probe, and not the reflection from the wall. We move the probe on a sphere around the antenna on the test, so we capture the radiation in all directions. We have full information about the radiated fields. Also, even if the absorbers reduce this wall scattering, it does not eliminate wall scattering. There's a bit of residual scattering, but if you use a directed probe, one that looks mainly at the antenna on the test and have low side lobes towards the walls and towards the ground, we can further suppress the residual scattering from the walls. Also, as we'll see in a little while, the measured field will be expanded in a mathematical series, and by adjusting, manipulating the terms in that series, we can further reduce the influence of noise. And finally, in every measurement, you have the problem that a signal goes from the AUT to the probe. Something is reflected from the probe, goes back to the AUT, goes forward to the probe. So on the probe, you have multiple reflected signals coming in. And one way to reduce that is to increase the measurement distance. And within the boundaries of the anechoic chamber, you can do that and still preserve all the other advantages. In practice, a spherical near-field antenna measurement facility may be implemented in many different ways. It can be the antenna on the test, which is stationary, and then you move the probe on a sphere around it. It can be the probe, which is stationary, and then you rotate the AUT over 2 axes. Or you can have 1 axis on each. Or you can have a half circle of probes or a full circle of probes, so you just need 1 360-degree rotation of the AUT to have a full sphere measurement. But all of these techniques, they rely on the same basic theory. And now I'll try to explain in 2 slides the theory of spherical near-field antenna measurements. And it has 2 ingredients. One is the spherical wave expansion, and the other is the antenna scattering matrix. So first, the spherical wave expansion. So if we have an antenna with a local port here, and we have defined a certain coordinate system for this, the field outside of the antenna can be written as an expansion over incoming waves, over outgoing waves if it's transmitting, and incoming waves in case it's also receiving. These functions that we have here, the spherical vector wave functions, they are fundamental solutions of the vector wave equation form a complete set. So if you apply to each of these the proper coefficients, you have a description of an arbitrary field. Now, you'll note that in this series, that index here is truncated at a number capital N. Mathematicians would say that this goes to infinity. But in practice, we can truncate it. And if we couldn't truncate it, it wouldn't be very practical. We would never be able to measure an infinite number of terms, right? So how do we truncate it? Well, all antennas can be circumscribed by a sphere of radius, and we can say the radius is R0. Then the number of turns that you need in that spherical wave expansion is given by the product of the wave number and the radius. So the electrical radius of the minimum sphere, and then to be certain, you add a few more. So here I have added 10. That's a golden rule which is used in the antenna measurement community. And what I plot here is sort of the power in the modes of different orders, and as you can see, at some point here, the power falls off very quickly. And this has to do with the radial dependence of the functions inside those spherical vector wave functions. Now, it's not impossible to imagine an arbitrarily small volume of current that would radiate an arbitrarily high number of spherical modes. One that would thus violate this rule here. But that radiator would be a core antenna. It would have a highly reactive field, low bandwidth, and if you could implement it in practice, it would have a lot of loss. So, for all antennas which are used for communication, for sensing, we can safely use this formula here. The second ingredient is the antenna scattering matrix. So that's an extension of the scattering matrix that you usually apply to microwave circuits. So it's establishing a relation between the incoming and outgoing signal on the physical port of the antenna to the coefficients of all of these outgoing and incoming modes in space. And the flow graph would look like this. So we describe the antenna in terms of the reflection coefficient. That's the usual input reflection coefficient. We have a number of transmission coefficient that relates the coefficients of the outgoing spherical modes to the incoming mode on the transmission line. We have a set of receiving coefficients that relate the outgoing signal on the local port to the incoming signal in space. And for a reciprocal antenna, these are closely related. And then we have all the scattering coefficients that relate an arbitrary incoming spherical mode to an arbitrary outgoing spherical mode. In short notation, we can write up the scattering matrix like this. I'm not sure who first came up with this scattering matrix for antennas, but for sure you can find it in this classical book by Montgomery, Dyke, and Purcell, one of the books from the MIT Radiation Lab series. Then we can see from that matrix description here that if we have a matched receiving antenna, the received signal on the transmission line are the receiving coefficients of the antenna multiplied onto the coefficients of the incoming spherical modes. That's actually an expression of some significance. In daily life, we say we take an antenna and we measure the electric field here. But actually, we don't do that. What you can measure is the signal on the transmission line connected to the antenna. And that signal is never the field in any particular point somewhere in front of the antenna or in the face center of the antenna. So what is it that we measure on the transmission line? Well, it's exactly this, the product of the receiving coefficients of the antenna and the amplitudes of the incoming spherical modes. And of course, if we know the receiving coefficient from a calibration of the antenna, from the signal we'll be able to retrieve the incoming coefficients. For a transmitting antenna, the coefficients of the outgoing modes are just the incoming signal on the local port times the transmission coefficients of the antenna. So now we have the two ingredients, we put them together. Here we have the transmitting antenna described by these coefficients of the outgoing spherical modes, or you could say also described by its transmission coefficients, and these are the ones that we eventually will try to determine from the measurement. And on the other side, we have the probe, where we know what the received probe signal is, the receiving coefficients of the probe times the coefficients of the incoming spherical modes. However, these coefficients are given in that coordinate system, the measurement coordinate system for the AUT, whereas these receiving coefficients are given in the coordinate system of the probe. So we need now to relate the coefficients of the outgoing mode on the antenna side to the incoming mode on the probe side, and this is done through a set of known rotation and translation coefficient. And when we put it all together, it looks like this, that the signal that we measure on the probe is this six-folded summation over the transmission coefficients of the antenna on the test, the ones that we want to obtain, and then some known rotation and translation coefficients, and then the receiving coefficients of the probe. So we need to have a calibrated probe. And the whole method of spherical near-field measurements is now to measure this probe signal in enough points around the antenna on the test that we can invert this formula and get the transmission coefficients of the AUT. And that's what we're looking for. Once we have them, we put them into the spherical wave expansion, and now we can find the field everywhere outside the AUT. This transmission formula, it's the central formula in spherical near-field antenna measurements, and it was developed in parallel, somewhat parallel, by Frank Jensen at the Technical University of Denmark and Paul Wacker at the National Bureau of Standards in the USA, and it's often referred to as the Jensen-Wacker transmission formula. By the way, in this formula, if you make the distance very large, this reduces, of course, to Friis's transmission formula. But this holds at close distance. Okay, a bit of history. So, the theory of spherical near-field antenna measurements was developed in parallel at what was then the National Bureau of Standards. Now it's the National Institute of Standards and Technology, and the Polytechnical High School of Denmark, which is now the Technical University of Denmark. And it's all documented in this Bible of near-field, spherical near-field antenna measurements. If you want to do something serious with spherical near-field measurements, you read this book here. And DTU also established, first it was an experimental, but then an operational measurement facility. At the same time, the European Space Agency saw a need for having accurate characterizations of the antennas they put on satellites and put up where you cannot repair them anymore. So a cooperation was established between the European Space Agency and the Technical University of Denmark, and that still exists in the form of what is called the DTU ESA, Spherical Near-Field Antenna Measurement Facility. So today that measurement technique is used from low to high directivity antennas, from small IoT antennas to large space antennas, from low frequencies around maybe 100 megahertz and at least up to 250 gigahertz. It's a commercial product that can be bought from several suppliers, and I think there are around 250 spherical near-field antenna measurement facilities around the world. And it's something where there's still a strong interest from both industry and academia. Last week we had in Madrid the European School of Antennas course on antenna measurements, and spherical near-field antenna measurements was part of this. There were 34 participants coming to this course, which is not bad. And even if you could say the core, the transmission formula is mature, it exists, there's still a lot of research going on around spherical near-field antenna measurements, and this is what I'll spend the rest of the talk discussing some examples of. And I could talk about many things, but I'll choose three things, and the first is the topic of antenna diagnostics. So for this purpose, I will go back to this soil moisture ocean salinity mission where we did the on-ground calibration at DTU. So you can see here the white dots are actually the antenna elements, and these are not just antenna elements in an array. These are individual antennas with individual receivers. So there's no array at RF. All the signal processing is done at baseband. So we had to measure each of these 69 dual-core antennas, measure the pattern for each of these to calibrate the whole system. And that was actually a years-long process first for preparations and then to do the actual measurements, and we measured one after the other and so on. And at the end of the campaign, when we came to that element here, the BC03 element, we noticed from its far-field radiation pattern that it had an unusually high level of cross-polarization, much higher than all the other elements that we had measured. So something is wrong. What is going on? And this is where you invoke what we call antenna diagnostics. So antenna anomalies are usually detected by inspecting the far-field pattern, but that doesn't tell you what is wrong in the antenna. To possibly find the cause of the far-field anomaly, you need to go to the near field and inspect the near field. What are the errors that we see in the far field? Well, a lower directivity or gain than what you expected. Main beam is asymmetric or it's squinted. High side lobe levels or even grating lobes. You have wrong polarization state, or you have, as we saw here, a high cross-polar level. Or you have a strong frequency variation that you didn't expect. Now, how do you go to the near field? Well, as you know, for any given near field, there's only one far field. That's a benign process. But for any given far field, there's an infinity of near fields that would give that same far field. So we need to find the right one. And once we've found it, what should we look at? Should we look at the electric field, the magnetic field, the Poynting's vector, the current? These are vectors, so which components should we be looking at, and should it be the magnitude or the phase of that component? And the answer is, of course, look at everything. Look at everything that can give you any idea of what is going on. And then we might find some manufacturing error, two panels which are not correctly joined, an incorrect position of the feed of a reflector antenna or reflector array, some damage that has been done during transportation or prior testing, a crack, a bump in a reflector, a crack on the edge of a patch or whatever, a soldering point that broke, or it could be some intricate coupling or scattering effect going on between the antenna element itself and the support structure on which the antenna sits. And finally, if the antenna is covered by a radome or some thermally insulating layer, which is often the case for satellite antennas, it could be an error in that. So here we have a little challenge with the spherical near-field antenna measurement technique. As I said, the spherical wave expansion, what we obtain, is valid outside a minimum sphere enclosing the antenna. And then we typically do the antenna measurements on a sphere which is a little further apart. Now, from that measurement, we can go to the far field, we can also go towards the origin, but we can never go inside the minimum sphere. The spherical wave expansion simply does not hold there. So if we look at it from the side, we cannot come to the surface of the plane antenna with the spherical near-field antenna measurement technique. If we had an expansion of the field in terms of plane waves, well, that would allow us to take the near field right back to the surface, because the near field and planar wave expansion is valid right up to where we have the surface. So during the years we were doing these testing campaigns, we were also working with antenna diagnostics. And there is a way that you can go from a spherical wave expansion to a plane wave expansion. And it's not that you should remember this formula, but the point is that the plane spectrum, the plane wave spectrum in any particular point in this spectral domain can be found from the Q coefficients that you have from your spherical wave expansion, And then you use some functions here, which are just the far-field versions of the sphere, of the functions that goes into the spherical wave expansion. So if you have the Q coefficient, it's a mathematical operation to find the plane wave expansion. It may sound a little strange. First you have an expansion that only holds outside a minimum sphere. Then you go to the far field, you turn it into another expansion, and that expansion can go inside that minimum sphere. But that's how it is. So in essence, we are taking all the discrete coefficients of the spherical wave expansion and we are turning them into a continuous plane wave spectrum. Of course, you can only find the plane wave spectrum in the visible region. You have far field quantities, so there's no contribution of the evanescent waves. So that means that the near field that you calculate in this way is not the exact near field, but it's the near field made up of all the propagating waves in the plane wave expansion. And since it was in the far field that you saw the problem in the first place, you'll probably also see the arrow in the near field of those propagating waves. It doesn't matter that we don't have the exact near field with the evanescent waves and so on. So let's look at the example here. The first row shows the X, Y, and Z component of the field just in front of the antenna here for an element that functions correctly. So this is A01, sorry, it's this one here. Huh? And this is then what we observed for that element where the far field was problematic. And you can see the X component looks, wow, okay. The Y component is way off and the Z component is also way off. But what is more important is we see that the problem is very close, right at the antenna element itself. That little white circle that you can maybe see, that's the contour of the antenna element. So we realize this is not due to some weird scattering or coupling with edges or hinges or whatever is on the support structure. This is right at the element itself. So we replaced that element and then the result was fine. But of course, it's not good to find an arrow with a problematic antenna element. The European Space Agency demanded that the manufacturer now take the antenna back and overlook and see what is wrong with that antenna element. And the antenna element is like a suspended patch which is proximity fed by a number of other patches that sits on small pins, and somewhere there was a soldering point that had broken. Yeah, the antenna had undergone vibration tests before they tested for radiation pattern, and one soldering point had broken in this element. Now, what do? You're about to launch a satellite, and we know that one element has a failure. What about the 68 others? Are they about to fail? Will they fail when we launch the thing? So the only action that could be taken was to take out all elements, put them under the microscope, and check all of those soldering points. And of course, that delayed the whole process by months, which is not nice, because when you, in a project like this, finally come to the antenna testing, all the allowable delays have already occurred in the design and in the manufacturing. When they come with the antenna for test, they want the results yesterday, negative time, there's a lot of pressure, many people are waiting down the line to mount that antenna on the instrument, mount the instrument on the satellite and get to the launch site. So it's a strange feeling having to say, stop, we need to do something here. But, I mean, we test to check for errors, so that's what has to be done. I'll move to a different topic now. I call it signal averaging with on-the-fly sampling. And that's actually, it's a sampling theory thing that applies to spherical near-field measurements, but could also apply to other types of measurements of spatially distributed fields. So, from the size of the antenna, we know the minimum sphere, we know the radius of the minimum sphere, we know the number of turns in the expansion, spherical wave expansion, and that also tells us how close we have to sample around the antenna. So, A spherical near-field measurement is made up of a series of circular measurements. So let's now think about having a sampling along a line here. It could be a circle on this measurement sphere. So we have a sampling step known from the electrical size of the antenna, and then we take samples at these sampling points. Now, if you took just one sample, you could think of it as one AD conversion in your receiver, that would be very much affected by noise. And for different noise levels, you could have anything from a usable pattern to a useless pattern. So what you usually do in that case is that you take a lot of samples and then you form an average of these. And then you know that if you make an average of, so I'll call the individual AD conversion, let's call it an actual sample. And then when you average, let's call it a nominal sample. And the nominal sample will then have a signal to noise power ratio, which is a factor better than the individual sample, a factor which is the number of actual samples which are averaged. So if you take 10,000 actual samples, average them into one nominal sample, you can increase the signal to noise ratio by 40 dB. So that's of course a clear thing to do. It's obvious that you should do it. But now we have to consider what kind of scanning scheme we use. If we have a measurement system, positioning system, that moves the probe to the sampling point and then stops and then do all the samplings there, it's fine. We have all the samples at the same point. It is in principle the same signal that we are measuring every time. Signal processing people would say this is coherent sampling. But it actually takes a lot of time to stop a positioning system at every measurement point. I mean, we could have hundreds of thousands of points around a large antenna. And to accelerate a positioner, make it travel, deaccelerate, and then fine-tune its position takes too much time. We would never end such a measurement. So what is often done is that we measure on the fly. So the positioner moves continuously, and then we have a position encoder that tells us now you are at the right sampling point, and then we trigger the microwave receiver, and we now start taking all the actual samples. But since the thing is moving, it also means that these samples, they are taken at slightly different points, and that could have a smearing effect on the obtained pattern. But fortunately, that can be corrected for, and I have the ambition to tell you how it's done. So, consider a signal on a single circle of a sphere. It has a Fourier series like this, with coefficients given by this. We have sampling points which are equally distributed over the 2 pi, and we need a number of samples which is more than, at least, or more than the number of unknowns. But now we're not taking samples at just single points. We are from a lot of actual samples taking over different points here, displaced by a little delta U here. We are forming an average, what we call the nominal sample. And if we put that nominal sample into a formula like this, we'll not get the correct coefficient, we'll get a non-corrected coefficient. Now, look at that formula here with the uncorrected coefficient. In that formula we have the nominal signal. Take that from up here, substitute in. Up here we have the signal. Take that from over here. In this way we establish a relationship between the uncorrected coefficient and the corrected coefficient. And when you do the math, it comes out wonderfully simple, that the correct coefficient is just the uncorrected coefficient times a correction factor. It looks like this, and you can see if we set delta U equal to 0, so all of these points are in the same point, well, then this cancels, this is 0, this becomes 1, there's no correction. If we only take one sample, capital L is 1, then this also reduces to just a correction factor of 1. And finally, for the n equal to 0 term in the Fourier series, which is the constant term, the average signal, this also becomes 1, because for a constant field, it doesn't matter where you sample it. Right? So this works very nicely. You can now do on-the-fly sampling, get the nominal signal, the uncorrected coefficient, use this formula, get the corrected coefficient, and thus the correct signal. All of this relies on having a constant sampling rate in your receiver, and also have a constant positioning speed. And the constant positioning speed is not always achievable. It will always vary a bit. But these are second-order effects, so that correction is anyway better than not doing anything. So here are some examples, measurements of a standard gain horn. The nominal sampling step is 2 degrees, and here we model taking 26,000 samples with the speed of the positioner. That means that we take those samples over an angular region, which is just 1% of the nominal sampling step. In this case, there's hardly any effect. You can see the reference signal here and the uncorrected signal. You cannot distinguish them at this scale. You have to go into particular parts of the pattern and look here. Here's the reference, here's the uncorrected. The corrected is up there. But these numbers are very small. In practice, with these parameters here, this is an insignificant effect. But of course, if you take more samples, so now we go to averaging 266,000 AD conversions into a nominal sample. Now the window over which we do this is 1/10 of the nominal sampling step. In this case, it starts becoming a bit larger. You can see the equivalent error signal of the uncorrected signal is now up to -40 dB. So it means it starts being at the level of other uncertainties in the measurement. So at least you should take it into account in your uncertainty estimate for the measurement. So here we have a notable effect. And finally, if we really want to have a good signal-to-noise ratio, and we average a lot of AD conversions using almost all of the sampling step to take over those AD conversions, in that case, you can see even on this scale, you can see that the patterns are not on top of each other, and we need the correction, and it works beautiful. Here's the reference result. Here's the reference result, the uncorrected result, and the red on top of the reference is then the corrected result. So here's a significant effect that needs to be corrected for. And usually when you have these kind of considerations in the measurement facilities, you would live with fewer samples, or you would lower the speed of your positioning system. So you would either compromise accuracy or you would compromise measurement time. But with this correction, you don't need to do that. If you want to read more about it, there's a paper here from last year, so you can. Finally, I want to talk about a topic that I've been very happy to work with for the latest couple of years, the topic of derivative sampling. So, looking again at a periodic signal, which could be the signal that we obtain when we do a circle scan in a spherical near-field measurement. It has, of course, a Fourier series. It's a periodic signal, truncated at some point. So we have a truncation number on the Fourier series, and thus there's a number of coefficients that we need to obtain. And if you space your sampling points equidistantly, you know that you can obtain these coefficients from samples of the signal at these sampling points. And this is an exact expression. You get the exact Fourier coefficients in this way. Now, look at that formula here. Take the derivative with respect to the spatial coordinate on both sides, and you see that the derivative of the signal is given by the same coefficients as the signal itself. It's clear that it's like this, but it means that we could also find the coefficient from samples of the signal derivative. Now, we don't intend to use one or the other. The question we ask is, can Fourier coefficients be determined from combined samples of signal and signal derivative at fewer than the standard number of sampling points? So if in each sampling point we sample both the signal and the signal derivative, can we do away with half the number of sampling points? And the answer to that question is yes. And this is an exact sampling theorem. This is not undersampling or compressed sensing or reduced order modeling or use of a priori information. This is a rigorous sampling theory. And you know who came up with that? Well, I don't know if he came up with it, but I know he mentioned it. Goes all the way back to Shannon. In Shannon's classical 1949 paper, he mentions somewhere down in the paper, one can further show that the value of the function and its derivative at every other sample point are sufficient. It was not the main point of this paper. He just mentioned it sort of with a left-hand comment, by the way. It's like this. And it's a concept which is well known in communities of communication engineering or information theory or even signal processing. But now for a couple of years, I've asked a lot of people in electromagnetics and in antennas and in antenna measurements whether they knew of this derivative sampling concept. And very few people have answered yes to this. And very, very few people have ever applied it in the area of electromagnetics and antennas and antenna measurements where I work. If anyone here has any knowledge of the use of derivative sampling in our field, please come and let me know after the talk. I would be very grateful to hear about that. But we have looked into it. There's a transaction paper here with all the fundamental formulas, and then Kyriakos Kaslis, a PhD student at DTU, has applied this to spherical near field antenna measurements. And I also have the ambition to tell you why it works. So again, consider this periodic signal. 2n+1 points are needed to find the 2n+1 coefficients with this formula here. But what if we now take samples of the signal only at half of these points? So n+1 points instead of 2n+1 point. What happens? Well, then from this formula we will not get the correct Fourier coefficient. If we try to determine the coefficient with negative index, a coefficient with positive index will fold down. If we try to calculate a coefficient with positive index, a coefficient with negative index will fold up. We have a liaison. But you can work out the formulas and see exactly what are the two that combines. Actually, for the n equal to 0, it's sufficient with capital N+1. Okay, thank you. I'm 5 minutes away. Okay, we do the same thing with signal derivative sampling, and again we find that we don't get the correct coefficient, but we get a combination of correct coefficients. And what is important is that these two coefficients are the same as these two coefficients up here. So essentially we have two equations with two unknowns, which can be solved, and we can find the correct coefficients. Putting it all together, we can find the following formula here for the coefficient from samples of a signal and the signal derivative in half the sampling points. And this can be used to speed up antenna measurements. Well, any type of measurements where you need to move the probe in space, because it may be much faster to do two samples at each point than physically move the probe. So it applies to measurements more generally than just antenna measurements. You can also take that analytic expression, put it back here, interchange the two summations. The inner summation can be worked out, so you find an interpolation formula. So the signal at any arbitrary coordinate from samples of the signal and the signal derivative at the sampling points. A series of interpolation formula like this, based on standard signal sampling, is what people call Whittaker's cardinal series. So this is Whittaker's cardinal series for sampling of signal and signal derivative. Okay, these are just one of many tests we have done. So it's a full sphere measurement of a standard gain horn. You would normally do sampling at every 5 degree. Here we have done at every 5 degree as a reference, and then also at 10 degree, we took signal and signal derivative. and then when we put them on top of each other, they agree fairly well from this, which is essentially a first try. The equivalent error signal is below -50 dB. The on-axis values agree very well. Now, we didn't have a probe that could actually measure the derivative, so what we did was that we took two nearby samples and then we formed the derivative from the finite difference ratio. But of course, we should look to have a derivative probe. And these are not strange antennas. You will see what we need is a probe which has one port where we measure the signal, so that's an ordinary antenna with a main beam on axis, and then another port where we measure a quantity which is closely related to the derivative, which requires a pattern with a null on axis. So we're looking for an antenna with a sum and a difference pattern, what in radar technology is called monopole antennas. And there are thousands of monopole antennas in this world to give inspiration to a derivative probe. This was a technique which was first developed for military radars, of course, and then it became much used in satellite tracking, and today it's in automotive radars and base station tracking systems and so on. I'll just show a simple example here. So imagine a square waveguide. I put in 4 feed pins into the waveguide. Depending on how I face the signal on these feed pins, I can create either a T10 mode, that measures the signal itself, a T20 mode, so the phase between these two are the opposite, right? So this measures a difference in this direction here, so that means perpendicular to the polarization, or the hybrid electromagnetic 1-1 mode, which measures the derivative or the difference in the direction parallel to the polarization. If we cut the waveguide open, use equivalent currents in the aperture, we can calculate the far field analytically, and they would show a sum pattern or a difference pattern of this type or a difference pattern of that type. We can also find the spherical wave expansions for these patterns, and they go like this. For a sum pattern, you have the typical M ± 1 modes, which are the strongest. For the difference pattern, it's the 0 mode or the M ± 2 modes, which are strongest. Again, for this one, M ± 2 or the 0th order mode. And because of reciprocity, these coefficients in the spherical wave expansion of the antenna when it's transmitting are also the receiving coefficients when we use it as a probe. So we have all the ingredients here. Nobody has yet made a derivative probe and performed a near-field measurement with a derivative probe. It's up for grabs. Anyone who does it will be the first to have ever done this. Okay, that brings me to the summary. So spherical near-field antenna measurement techniques, they constitute the most accurate technique for experimental determination of radiation from antennas. It's my claim, at least. For space antenna technology, the accuracy requirement can be of the order of 1/100th of a dB. 1 dB measurement accuracy is no problem. 10th dB of accuracy, start being a bit careful. 100th of a dB accuracy, you need to be very careful. The core of the spherical near-field antenna measurement technique is mature, but still it continues to be an area of much research and development, as I hope I have illustrated with 3 examples here. So finally, I just want to tell you that we are a group of people interested in antenna measurement, and we meet in this association called the Antenna Measurement Techniques Association. We have an annual symposium. This year it will be in Tucson, in Arizona. And if you cannot come there, you could check out this recent paper. It's an online open access paper by the European Association on Antennas and Propagation called Antenna Measurement Challenges and Opportunities. So a lot of experts has given their view on what is actually state of the art for different type of antenna measurements, what are the challenges and what do we need to do in the near future. So if you want to have an overview of the state of art of antenna measurements, read that paper there. So with this, thank you.
Okay, thank you, Olav. Questions from the audience? Up there, did we have wireless microphone somewhere?
It's okay.
Okay.
Just characterize you need that advanced matrix show.
For the probe, yes.
Yeah, for the probe. So this is probably something that the manufacturer will not give you. So how you characterize it by yourself in a simulation or?
No, it's usually not. It's usually not by simulations. It's by measurements. And the people who do that for you will charge you a lot of money to give you calibration data for the probe. It's not given for free by the manufacturer. You probably are asking, how do you do that now? Because then you need another probe. But this you can do in a far field measurement setup. In a far field measurement setup, you don't need probe correction because you're looking at, now the probe is the antenna on the test, so you're looking at this in a very small angular region. You can assume that in that setup, what we call the auxiliary probe is like a version type of it. But you're right, you need the receiving coefficients of the probe to correct for the influence of the probe on the signal. Yes, it's important.
And just connecting and if you would like to have the full matrix and even the back reflections and so on, this is also what you really do.
No, you will never try to determine the scattering coefficients because even for a small antenna you can have tens of thousands of receiving coefficients. I didn't point it out, but you probably noticed that the number of scattering coefficients is the square of the number of receiving coefficients. It would be practically impossible to determine all those scattering coefficients. I mean, mathematically you could do it and you could correct the transmission formula for the multiple reflection, but practically you would never be able to characterize all of those scattering coefficients. So the multiple reflection is a source of uncertainty, so you list it in your budget of uncertainties and measurements. I've never seen anybody trying to incorporate that into an actual measurement.
Okay, I think we have,
Yeah, I wonder if you will synergize with the quantum computing people because they have been stagnated for a decade or so now. I think noisy intermediate stage quantum computer because of the noise problem. And the noise problems, when they can remove, they can help the people synergize with those people.
That could be a good idea. Yes.
And
I
also,
think you need to give me some names.
another question I have is that do you use a phase lock loop to improve the signal isolation?
Well, we use, I mean, the usual microwave instrumentation is either microwave receivers, which use phase lock loops, or vector network analyzers, which I guess do that also. Yes.
Okay, the third question I have is that from some of the equations, you can determine or retrieve the coefficients if you use the knowledge in the inverse source problem. Because inverse source is not unique, but if you take a subset of the inverse source involved, you can get unique solutions. Whether you can look into that possibility of making your measurements more accurate by using knowledge in the inverse source community.
Again, we're open to all ideas. This I would probably like to discuss a bit with you afterwards. But I think the spherical wave expansion is actually a unique characterization of the field. So, can we talk afterwards?
okay, I think up there was the next question.
Just a quick question. Okay, so my question is that you mentioned that you can transform a spherical expansion to a plane wave expansion.
Yes.
I was just wondering, to get closer to this,
So, you were just wondering if.
So our question is, does this affect the number of terms that you need in the original expansion in some way, the requirement, or does that?
No, because as you saw in that formula, I can calculate the plate wave expansion as in as dense a grid as I want from that formula. It's just about evaluating these K functions for different arguments. So I can calculate the plane wave expansion in any demonstration you want from the set of Q coefficients. And the set of Q coefficients, the number of these will be determined from this sphere.
But the same is right. So it's the same number of terms.
No. You can calculate any more points in the plane wave expansion than what you have Q coefficients.
No, it just makes the original expansion really more terms for it to give you accurate results.
No.
Okay, thank you. Okay, thank you. We are half past and next sessions are about to start now, so we need to close this session. Let's turn to speaker again.
An extra question that is relevant to the school on since I read that the frequency starts from 100 megahertz.
Yes.
I ask it because I have a PhD student that works on English channel, and he believes these are antennas and should work on